just start introducing the first speaker of the day. So we have Razvan Pascanu. Razvan, maybe you could just introduce yourself and tell us where you did your PhD.
Yes. So as I said before, I'm Razvan. I did my master's at Jacobs University in Bremen, and then my PhD with Joshua in it wasn't Mila back then, it was Lisa, but now Mila Institute. And after that, I joined DeepMind, where I've been for the last 4 to 5 years, doing research in different subfields of deep learning and reinforcement learning. Okay, so let's.
I would just have one mention. So for the listeners, please do not use Slido as a chat room. So for chatting, please still use Rocket Chat. For Slido, we use it only for questions for the lectures. And you have also the possibility to upvote people's questions in case you want to make sure that question gets at the top of the list and it gets answered. So please do not post chat messages on Slido. Thank you.
Okay. And now, so going back to the lecture, just a few notes before I start. I guess there's a Slido, ask questions there. If there's still things that I don't get to, please, you can ping me on Rocket Chat or even send me an email and I can discuss things further. The lecture itself is going to be split in 2 parts. In the first one, we're going to start talking about the learning process and representation in deep learning. In the second part, I'm going to focus a bit more on parameter sharing and sort of different types of architectures. And we're going to have a break between the sections where I can answer some questions. Obviously, presenting a whole deep learning doing a proper introduction to deep learning in 1 hour is pretty hard. So I'm going to be extremely selective on the kind of things I'm going to talk about. So let's start by sort of introducing the framework, and we're going to consider the simplest scenario, which is supervised learning. Most of you probably already know this, but the big picture is you have some input space, you have some output space, and what you're looking for is a function that takes you from the input to the output. In our case here, denoted by h. And we want h to be a good predictor. So we want for a given input to get the kind of output we would expect, that the data kind of tells us that we would want. And depending on the output space, if the output space is continuous, this becomes a regression task. If the output space is a categorical, then this will be a classification and so on. When we're talking about parametric models for learning, what we mean is that we have this function, instead of going directly from x to y, it actually goes from some parameter space theta. So the function gets theta, x, and has to produce y. And then the game becomes discover the right parameters theta, such that when I plug this theta and x, I get the right output that we want. And just as an illustration, for a linear function, the function itself is just the product between the w, the parameters, and the input x. And when we're trying to learn, what we're trying to do is we're trying to find theta such that we're minimizing some loss. And the loss typically is just the expected distance between the output of the function and the label or the target that we have from the data set. Now, 2 important questions is how do we, what is a good parametric model, or what form should this function h should have? And then the second question would be, how do we find the theta? So let's start with the first one. In this particular lecture, we'll exclusively focus on neural nets. These are a family of models that are very popular nowadays and work really well. And at a high level, what a neural net does is basically it's a bunch of linear projections followed by some nonlinearity. And for simplicity, and the most widely used nonlinearity is rel, which simply returns x if x is positive and 0 otherwise. So you compose these linear projections and nonlinearity one after the other to form your neural net, like here. So h of x becomes L3 of L2 of L1, where each of this L stands for layer. Each of these functions is basically just a linear projection followed by the nonlinearity. And I guess this might be known for most of you, but the reason you have the nonlinearity is if you would remove the nonlinearity, all of these linear projections would collapse into one single one. So the nonlinearity adds you expressivity. In particular, if we're talking about the ReLU nonlinearity, what it does is basically gives you a piecewise linear function out of it. And if you consider a single layer neural net with ReLU activations, then you can think of each ReLU unit as being a hyperplane that is splitting the space. And what you get out of it is you get this linear function that has different linear responses on different parts of the input domain. And sort of this gives you like a very intuitive feel of how this one layer neural net works. So you can partition the space in different ways, and then for each partition you can sort of change the linear response a little bit given the units that are actually active within that linear region. This also gives you a way of thinking about the expressivity of the model. So we know that neural nets are universal approximators. In this case, it's obvious. You can always, if you have an extremely large number of linear pieces, or you have like infinity of linear pieces, you can arbitrarily well approximate any kind of surface. And you can get a sense of the expressivity of neural nets because you can actually count the number of linear regions that you have. So in this particular very simple case of a one hidden layer model, you can use, it's all about counting into how many regions you can split the space with k hyperplanes, and this has been solved in geometry a long time ago. So this would be, the answer comes from Zalaski's theorem that gives you the exact number of linear regions that the maximal number of linear regions that you can achieve. One big emphasis in deep learning, though, it's in having deep models. And then I guess one question would be, why do you need this depth? So one thing that you can notice straight away is if I go on the second layer, then and I'm looking at what this a unit on the second layer does, like each unit itself becomes a linear, a piecewise linear function. And the interesting thing about this is that piecewise linear functions that can intersect in more than 2 points. So just for context, the Zalaski's theorem that it helps you count the number of regions heavily relies on the fact that two lines only intersect at most 1 point. And you can use this, and through induction, you can actually start counting the maximal number of regions that you can have. But now in a deeper model, if you have these piecewise linear functions that can intersect in arbitrarily many number of points, you can augment a lot more the number of linear pieces. So one way to try to think about what this thing does is to think of each layer as folding the space into itself. And this is sort of like a very natural way to try to think of how you gain this expressivity, and also how you can reduce the complexity of the problem. So I have here like a toy example where, assuming this is a decision boundary that you have, if you find a first layer that somehow folds the space first like this, and then a second layer that folds like this, then on a third layer, the decision boundary that you need to learn becomes much easier. And when you go back to the input space and you unfold the space, you can get sort of the complicated decision boundary that you had. So,
Razvan, if you could just, sorry for interrupting, it seems like the screen is not well seen.
The screen.
Let me just check with Raresh. Just give me 2 seconds. On the channel, it seems like it crops the left side of the
Okay.
slide.
Not sure what to do.
I don't think it's from us.
I mean, I could. No, if I exit present mode, I guess it's not going to be any better.
No.
No.
Okay.
I just need to be. Okay. Okay. So, and the nice thing about sort of this idea of how you fold a space is that you can increase the number of linear regions that you had by a large amount. So in particular, you can think of chessboard kind of style of folding, where you kind of fold each square on top of each other, and then when you draw a decision boundary, even a linear one, in this folded space, and you unfold it, you get this replicated in every square that were folded on top of each other. And in this paper that I've cited here, you can actually show that if with the same number of parameters, if you arrange those parameters in a deep fashion, you can get exponentially more linear regions than you would get with a shallow model. So this gives you one sense in which deep models are better than shallow ones. Is you have this exponential gain in expressivity, and it also gives you like an intuitive way of thinking of how neural nets work by thinking of them of just folding the space in different ways to make the decision boundary that you need to draw on the folded space much simpler than the decision boundary that you have to draw in the original space. Of course, like all of these things have caveats. Besides the fact that the neural net doesn't really fold the space exactly. Basically, it can also project an entire region of the space to a point, which you can't do when you do when you fold the paper. There's also other aspects of it. So in particular, if you take this kind of constructions that help you maximize the number of linear regions, and you look to see what these linear regions are, you would notice that there is a lot of symmetry in these linear regions, which makes sense because they come from this folding of the space, which means that while you've increased the number of linear regions exponentially, actually these regions are not independent of each other, and they can't just be oriented any way that you want. And this actually is it's a good thing, because otherwise the models will be able to fit everything perfectly, and you'd end up in overfitting everything. But this also says that just counting the number of linear regions is not sufficient. You need to describe how these things are restricted, and we don't yet have the machinery for that. So these are sort of open questions. And actually, I'm a bit my gut feeling right now is that most of the measures of complexity or expressivity that we have for neural nets are incomplete, and they're sort of taking this kind of a crude view on one aspect of it, and there are a lot of caveats for any of these measures, and the same holds for this region counting approach. The other thing that I wanted to mention, and another sort of intuitive way of thinking of neural nets, is sort of this idea of having more and more abstract features. This has been popularized. So Matt Zeiler, Hong Agli, a bunch of other people have been talking about this, where you almost have this perception, you know, the same way like how people were talking about the brain, of you having the grandmother cell and Jennifer Aston cell and so forth, like these cells that are detecting particular patterns in the input. The same has been said about neural nets, and you know, you can go somewhere high in a neural net and you can say, okay, this neuron is responding to eyes of a particular shape orientation. This neuron is responding to noses or mouth or whatever. And you know, as you go up, these concepts become more and more complex. So this kind of visualization are usually done using doing saliency maps on trained neural nets. There's this interesting paper about a paper from Sergil and Joshua that looks at what happens if you interpolate a different layer of a deep autoencoder, and shows that actually if you interpolate in higher layers, then this interpolation becomes more semantically meaningful. And this is another way, like the work is trying to argument the fact that, you know, the higher you go in the model, you have more abstract features that respond to more complex patterns, and moving, you know, changing the value of the neuron, you're moving in a manifold of that particular complex class of patterns. But again, as with any kind of intuitive understanding of neural nets, there are many caveats. For example, you could argue that a particular neuron is responding to eyes, but then you can easily construct a counterexample where you can take an image of a panda or whatever you want to, and you add some particular kind of noise, and you can make that neuron to respond strongly to it. So I think it's a very conceptually is a very useful way of thinking of how representations are built in neural nets, but you need to be aware that attaching semantics to representations is not that easy, and there's like all of these kind of caveats that you need to consider. Yeah. And then for the second part that I wanted to touch on is, okay, we know the neural nets are very powerful. They can represent lots of things. They're very flexible. But in order to do that, we need to find the right parameters. And the question is, how do we find these parameters? And there are two sides of this question. So first of all, the particular thing that you want to minimize, the loss that you want to minimize, is an expectation. And ideally, you want to compute this expectation over the entire input space, because you want to minimize the distance. You want to minimize the distance between the output of your model and the desired target output on all possible inputs, because you want to be able to deploy this model and get meaningful answers on inputs for which you don't know yet the label. But this is something that's intractable, right? You can't compute this expectation. So what we have to do is we have to replace it by a sum over the data points that you actually have. And because of this change between the expectation because of this approximation of the expectation by the sum, then you have these two sides of the coin. So one is the optimization side of it, where the question is, okay, how do I minimize this approximate loss the distractible loss that I can compute to get zero error? So how can I minimize the training error? How can I make my model to predict the right thing on the training set? But then the second side, which is actually the part that we care more about, is sort of the learning and generalization side, which is how do I minimize distractible loss in such a way that actually the model behaves well on data that you don't have access to yet, on test data, on data that you haven't used to train the model. And I'm going to talk about these two sides separately. So let's start with the optimization. So how do you optimize the neural net? So this is a very nonlinear function. The usual approach we do optimization and this kind of things is through an iterative process. So what we do is, given a particular set of parameters, we can approximate the loss at that point. So I just jump to the formula. So you can, at each point in space, you can approximate the loss by a first-order Taylor expansion. And the reason to do this is because a first-order Taylor expansion is a linear function, and we know how to minimize a linear function. The issue with it is, of course, the first-order Taylor expansion is only true locally to the, so it only approximates your nonlinear function locally. So what you have to do is you have to put a trust region. So you have to say, okay, I will approximate this surrogate function, this first-order Taylor, which I know how to, but I'm only going to look for a solution within this epsilon ball around the original theta, where this approximation actually reflects the function I want to optimize. So if you do this, and because of the constraint, you try to push the constraint up using Lagrange multiplier, and you do a little bit of algebra, what you get back out of it is the usual update that we normally do. So you get the HGD step, which says, basically take a small step in the direction of the gradient, and the direction of the moving in the direction of the gradient is what would minimize this first order Taylor expansion. So at a high level, this is sort of the and then you have to apply this again and again and again. So this becomes an iterative process because you can only move locally within this epsilon pole. So you have to do this many times until you converge. And this gives you the workhorse of learning in neural nets. This gives you HGD or gradient descent, which is the main tool that we have. And yeah, you can think of it as just leaving, on a weirdly shaped surface, leaving a little ball running loose, and then gravity will take it to a local minima that's close to it. The maybe more mechanical side of things is, okay, we know sort of what we want to do. So we want to compute these gradients iteratively and apply them, take small steps to them. One question might be, okay, how do we compute the gradients in this model? So one obvious thing is, if you look at the gradient, you can decompose it based on the chain rule. So it becomes a product of Jacobians for each function in these compositions of functions, because neural net in the end is just a composition of very many little functions like linear projections and nonlinearities. You can compute the Jacobians of each one independently, multiply them, and this gives you the gradient. I think these are kind of obvious stuff, but the one thing that I wanted to point out, because I find that a lot of people actually don't think about these things too much, is, for example, there is a lot of talk about backprop, and backprop is just a chain rule. So I wanted to highlight what is special about backprop versus general. So one thing that you normally do when you have to compute these gradients, you start from the top and go towards the bottom. And I guess the question is, why do you do that? Like, you could potentially compute the chain rule in any order that you want. And the reason you do that is because if you start at the top, and because the loss is a scalar, the first term of this product becomes a vector. So the gradient of L with respect to the output, it's a vector. And the nice thing about this is that as you go backwards through the model and you keep multiplying these Jacobians, you end up needing to multiply a lot of vector matrix. So you need to do a lot of vector matrix multiplications, which can be actually cheap, and they use a lot less memory. While if you'd compute the chain rule in any other order, you'd end up multiplying matrices, which require a lot more computation and a lot of more space. The other thing that I wanted to mention is just sort of mechanically, what do these gradients do, especially when you have multiple examples and you average them. So a gradient, as we all know, is looking at the limit of, okay, if I add epsilon to my weight, how is my loss going to change? And we compute this independently for each example in the data set that we have. So you can think of this as, for each example, we're asking the question, should I increase or decrease my weight in order to minimize the loss? And we do this independently for each parameter of the model. And each example is kind of voting the way they want things to change, right? So some examples will say, okay, increase the weight, and some examples will say decrease the weight. And what this does is this creates a sort of tug-of-war dynamic. So now basically different examples are fighting over the weights and trying to push them either to increase or decrease. And the way learning happens is by playing this tug-of-war games many times for the same parameters and ending up to some kind of equilibrium. This kind of intuitive way of thinking of this also explains the need of having a randomized initialization, because if all the weights would be initialized exactly the same, then you'd be playing exactly the same game for every parameter, and then everything would be moving exactly at the same speed in the same direction. So all the weights would always stay in sync, and you would not be able to specialize different ways to do different things. The way specialization happens is by a different subset of examples winning a parameter over and deciding the direction it has to move into. The other thing that I wanted to mention here, and sort of just as a discussing sort of the implication of having this kind of tug-of-war dynamics in order to do credit assignment and to do specialization of weights to solve different parts of the network, is to think of what happens when you have multiple tasks. I mean, the same thing happens when you're thinking of different examples, but talking about multiple tasks becomes easier. So we had like an interesting work with Tom Scholl that I think people can check out later. But the bottom line is, if you have interference between these tasks, or if you have interference between different examples, then what happens is some examples might end up dominating the others. And then this would lead for learning to learn different modes of your data, or learning different aspects of your data sequentially. So even though you're presenting all your data set at the same time, say you do full batch, you provide all examples at the same time, actually, if you check how quickly you improve on different parts of your data set, you'd see that it's not happening at the same rate. Some things will learn really fast, and some things will only learn after these things have learned and you've converged on some aspects of your data, and that's when you start learning different aspects of the data. And this comes from all of this interference and all of this tug of war. And this is important because what it leads to, it leads to the data inefficiency that we observe in deep learning. So what happens is, even though I've learned one particular set of examples, so I know how to classify between 1 and 2, but I don't know how to distinguish with 3, because of the tug-of-war dynamics, you still have to evaluate and recompute gradients on all examples, because as soon as you stop evaluating the easy examples that you've already learned, then you don't have that pressure that keeps equilibrium, and then the hard examples will just push all the way towards them. And I just wanted, I'm not going to talk about this, but like this can lead you in ways of thinking about why is important to have IID data, independently identically distributed data, and sort of what that means if you try to learn things sequentially, like you need to do in continual learning and so forth. And basically what it says is sort of this tug of war dynamics can only work in IID settings, or it can only work when all the data is available at the same time, so that you can have the right pressure. And the way we're learning right now, there's no explicit knowledge composition. So all the knowledge that needs to be learned needs to be present at the same time. And this is sort of a failure, or this is sort of a weakness of the typical paradigm of learning and the way we do credit assignment. And this can lead to things like catastrophic forgetting. And it would be quite interesting to keep the performance that we have with neural nets, but find alternatives way to doing credit assignment that can allow for sequential learning and can actually allow for more data efficient learning by not enforcing all examples to be present in order to have this equilibrium in this kind of push and pull kind of dynamics. The other aspect of it, and this is maybe the typical thing that you would think of, if this is the optimization process that we have, as I mentioned before, this kind of converges to the local minima that you're in, right? So if you're in a particular valley, you would go to the bottom of that valley. There is a good question of why is this a valid answer? So this was a reason why deep learning wasn't that popular in the 90s. Basically, people were looking at loss surfaces like the one I've depicted here that are very rugged. And if you leave one of these iterative algorithms run on one of the surface, you'll just converge to the first minima you see, which could be far from optimal. And you don't have any kind of guarantees, and you don't have any way of fixing it. So it feels like it's a very unreliable. Likely a few people weren't necessarily worried that much about this, and they just kind of pushed, and empirically it turned out that this is not as big of a problem as it might look when you look at these things. And partially this reason is because our intuition of, the intuitions that I was trying to explain earlier was like, okay, letting a ball kind of fall on kind of like a rugged surface, or most of these things come from low dimensions. Whenever we try to visualize and think about the loss surface and the geometry of these models, we always think in low dimensions because it's really hard for us to imagine really high dimensional spaces. But when you move to high dimensional spaces, things actually change quite a bit. So it turns out that when you're in high dimensional spaces, actually these loss surfaces are not as bad as they might seem. And at least locally, they seem to be quite smooth. And it seems that most local minimas are connected to each other, and most local minima actually have the same performance. And there's some statistical physics reasons for this, and there's some citations here for people that are more interested in this. Of course, things are never as easy as they seem. So even though locally there is a lot of evidence now, and there's some theory that relies on heavy approximations saying why you shouldn't be worried about it, you can obviously construct counterexamples, particularly if you move away from zero, where the loss surface can be arbitrarily bad. And on the left side, we had this little paper where we showed that if you give me an image of whatever you want, I can find in the loss surface of an MLP trying to learn MNIST or whatnot, I can find an area of that loss surface that looks exactly like the image that you want. And you can prove that for any image, you can find this area in the loss surface that looks like whatever you want. So the loss surfaces of these models are extremely complicated and can be very ill-behaved, especially far away from zero. However, so far, it seems that there is a particular region in the space where things are quite well behaved, and that's why things work well. And I'm not going to talk about it, but obviously I've been talking mostly about gradient descent. You can augment this thing, so there's a lot of variants of optimizers. Most of them, what they're trying to do is they're trying to take into account the curvature, how quickly the loss surface decreases or increases, to figure out what is the right step size that you need to take. And because this is a very expensive process, there's many ways you could approximate this optimal step size, and you get very different algorithms. So we've talked a lot about optimization. So this is how do you get zero training error? How do you make sure that the model produces exactly the target output on the inputs that you have on your data? But learning and generalization is something slightly different. So for example, you have these data points and you try to fit a model that is trying to predict the output. You can look at what would happen if you try to do a linear fit, and it will look like this. You can try to do a second order fit, and you can try to do a ninth order fit. All of this, I mean, as you increase the order of the polynomial that you're using to fit this data to try to find the right polynomial that represents this data, you would get a better and better fit, right? So the ninth order polynomial has 0 error. But somehow, if you look at the data, it doesn't seem right. So it seems that the ninth order fit, it seems just not to do the right thing. And this is sort of what can happen with neural nets as well. So with neural nets, what could potentially happen is you can get 0 training error. You're doing exactly the right predictions for the data points that you have in a training set. But when you move to a new data point that you haven't seen, then the model can be arbitrarily bad. And this is not what we want. This is not what we want to use the model for. The main goal is to be able to predict well on new data. And one way, and this is particularly a problem because neural nets are universal approximators, right? So, in polynomials, like you need to go pretty high degrees in order for you to get very complicated functions, but neural nets are extremely expressive. As I mentioned, the number of linear regions that you get grows really, really fast, grows exponentially with the size of the model and the depth of the model and all of these things. So then how do you make sure that you actually learn something interesting and you don't just fit the data without being able to produce meaningful predictions on new data points? So one aspect of it is the same trick that I mentioned for the polynomial, is you can restrict the size of the model. So as you restrict the size of the model, the class of functions you can represent becomes smaller and smaller. So there are less chances for you to find this thing that perfectly fits the data but doesn't work outside of the data, that doesn't generalize. Another way to think about how you are constraining the expressivity of the model during the learning process is to realize that if you fix the number of steps that you can do in this iterative process, it's almost like fixing a it's like restricting yourself to a region around the starting point. So now you can only reach the functions that are within this hypersphere, centered of where you started learning. And this is another way for you to restrict the space of functions that you would be able to represent through this process of learning. And in particular, this idea of restricting the space by the number of steps that you can do is extremely popular, and it's what people would call early stopping. So, and the way you do this in practice is you have the training data that you're training on, and you have some other data that you're not allowed to train on, and you use that to estimate how well you do on new data that you've never seen. And you compute this regularly, and as soon as you see that evaluating the validation loss, evaluating this data that you're not computing updates on, as soon as you see this loss going up, it means that you're starting to overfit and you stop learning. So this is like a way of identifying what is the number of steps that I need to do such that I learn the problem that I care about, but I don't learn it to a point where I'm just fitting the training set without generalizing. Yeah. So this is early stopping, and I like sort of this tagline that learning is about minimizing an intractable function that you don't have access to by optimizing a tractable approximation of it. And you always need to be careful, because your goal is not to get 0 error on this tractable approximation, but it's actually to get good performance on this intractable one. Another way to try to correct for this issue of overfitting is by regularizing. And the way you can think of, there's many ways you can introduce regularization, and you can understand the regularization. I think typically people approach this from a probabilistic perspective. In these slides, I try to stay away from it for a bit. So one way to think about it is you add an additional term. If you're thinking in terms of loss surfaces, what this could do is, imagine you have the loss surface of the function that you're trying to minimize, which is the thing in the middle, and then you have a regularization term, which is just computing the distance to 0. So this is a very well-behaved loss surface that has a single global minima of 0. And now when we're composing, when you're adding these two terms together, when you're composing the regularization term with the function that you're trying to minimize, you're changing the loss surface. So you're adding to this these two surfaces, and what you're doing is you're prioritizing one of the minima of the model that you're trying to train over the other, because one of the two minimas that you had before is closer to zero. So you can think of regularization as a way of prioritizing which kind of minimas you prefer. So you know, in this particular case, with the simple L2 regularization, what we're saying is we're preferring minimas that are close to zero. There's going to be more talk about this from Michal Belkin. So recently, I think we've started improving our understanding of learning these models, and it might be that this simple kind of view that I presented before with early stopping doesn't hold. And actually, we are in a very different regimes when we're training neural nets, and this is sort of represented by this double descent idea. But I will leave Michal to talk about this during his lecture. The other thing that I wanted to mention is that there is another aspect of regularization that happens in learning. So we've been talking we've been talking a lot about gradient descent, where you have all the data, access to all the data. In practice, what we use is stochastic gradient descent. So for scalability reasons, what we do is we don't compute the gradient on all the data, but we pick a random subsample of it, and this adds noise to the updates. And it has been argued that this noise is actually extremely helpful. So what the noise does, it helps you to escape minimas that are very sharp. So you can only converge to minimas that have a very wide basin of attraction. And there is some reasons to believe that if the basin of attraction is wider, then this the solution to your optimization problem is going to generalize better. So there is an implicit regularization that comes from the stochasticity of gradient descent. And this is a very powerful intuition and way of thinking about neural nets. I think there still needs to be some work in formalizing better this hypothesis. In particular, in a lot of papers that I'm aware of, many times the sharpness and flatness is represented by the largest eigenvalue of the Hessian or by other properties of the Hessian. And the issue with this is that actually in neural nets you have lots of flexibility, so you can change the curvature around the point where you are without changing the function. And all it means is not that the hypothesis itself is wrong, but it's a bit imprecise at the moment. We don't really have a definition of what sharpness and flatness means, particularly in high dimensional spaces. And because of this, it's a bit hard to talk about this hypothesis in formal terms. This is not sure if there are any questions or if I should just go ahead.
Yes, there are actually many questions. I was waiting for you to take a break.
Okay.
I'm not sure if I can share the screen though. Just a second. We have it here. I hope you can see it. So I think, thank you all for asking questions. You've been very active on this. And thanks, Razvan, for the great first segment. So Razvan, can you see the questions? So
yes.
I think there are quite a few asking about nonlinearities. So when do you use ReLU instead of sigmoid?
Yeah. So
compare ReLU with leaky ReLU, just to combine with a later question.
Yes. So I think you'd always use ReLU in a feed-forward model. You'd use sigmoids for recurrent models, and I didn't really introduce them. But the problem is, if you in recurrent models, you can have this exploding or vanishing gradient problem that I'll talk about later. But the problem is, if you have ReLUs as your nonlinearity in a recurrent model, then as you're going forward, so not when you're computing your gradients, as you go forward, you can get your representation to explode. And that actually makes ReLU and recurrent nets not match together very well. You also would use sigmoids when you need to have a probabilistic interpretation of your unit. So you want to, like, for example, in gating, where you want to, for that particular thing to represent how open or closed the gate is in things like LSTMs or like attentions and all of this kind of stuff. So, sigmoids are still around and they're still very needed, but for just typical feedforward processing, I would always use ReLU. And then for leaky ReLU versus ReLU, there's many variants of ReLUs nowadays. In my experience so far, they're kind of equivalent, and for some of them, like I don't really buy some of their argumentation that they should actually be better. There's lots of works, there's lots of theory, but I think empirically they haven't shown to work better. So I think it's just a matter of choice. Different researchers would use different activations. It's completely fine. It seems that are to a certain extent equivalent. So yeah.
Okay. So should we move on to next? How do you decide how many neurons and layers are needed for a certain data set?
Right. So I guess it depends on the data set. If we're talking about large data sets, as people normally use in vision and so forth, like think ImageNet or so on, I would go larger is better. And for large data sets, I don't think this is really a problem. It's more about a question of compute and what your card can support. For smaller data sets, you might need to be a little bit careful. For a while, it used to be that everyone was using 3 layers. That was the magical number, and that was fine. And I guess for a small data set, I would just go for 3 layers from instinct. Another rule of thumb that a lot of people do, and I think it's a way of thinking of things, is you just try to borrow an architecture from a different published paper. So, you don't make your ResNet, 53 layers. It doesn't make sense. You either use ResNet 50 or 18 or whatever, one of the existing.
Okay.
Next.
So slides, yes, we will share the slides as soon as we manage to get them. Next. Trade-off of complexity and approximation power between ReLU and other activation functions like tanh and sigmoid.
Yeah, so I'm not necessarily aware of works that actually, I'm sure there are, but I'm not on the top of my head. I'm aware of works that look at sigmoids and sort of expressivity within sigmoids networks, and works that look at ReLU nets and expressivity with them, but not necessarily comparing the two. I would say the issue people try to avoid sigmoids and tanh is not sort of a problem of expressivity, but it's a problem of learnability. So you have to balance these two things. It turns out that ReLUs are so much easier to learn that even if the sigmoid or tanh would give you more expressivity, I would still not opt for them because I would not be able to optimize them. So, yeah.
Okay. People liked the paper folding analogy. Could you use the same for SVMs? Or if not, what would be a more appropriate one?
This is a great question, and I don't think I have a good answer on top of my head just because I haven't necessarily thought about SVMs that much. Potentially, yes, but I would have to think about it. Maybe this is a question to be taken offline and discussed on Racket Chat or something like that.
Okay, cool. So the next one, I guess you've covered already the comparison with leaky ReLU. Can the choice of using a parametric or a non-parametric model depend on our input data properties?
Yeah, obviously, like these are very different family of models, and they work differently. So, like if you'd have a small data amounts, a non-parametric model would definitely work much better. And there's always ways of combining the two. So there are some papers on this, and I think this direction going, but complementary learning systems where you have both a non-parametric and a parametric side, and you're trying to leverage best of both. But yeah, definitely data depends a lot on what model you should use.
So maybe we'll just take 2 short ones and then we continue. So can you cite papers that give reasoning on how to split data into test, training, validation? Or should we rely purely on rule of thumb?
Yeah, so I think this is a topic that needs to be revisited. So there are some papers, again, ping me on Racket Chat and we can try to find citations. There might be some papers, but they're usually like older papers that talk about really small data sets where these things becomes quite important. I think when it comes to large data sets, there's no papers that actually done any kind of analysis of how you should split the things. It's more like a rule of thumb or whatever the data set creator decided. Yeah.
Okay. So we will skip again the one with the ReLU and leaky ReLU, and probably we'll take the last one now, and we'll continue after the next segment. Could you please elaborate on how can you change the curve?
Yeah. So I mean, like, let's take a very simple example. You have a ReLU net. One thing you can do is you can multiply, if you can multiply the weights on the first layer by alpha, where alpha is positive, and the weights on the next layer by 1 over alpha. And what this would do is this would not change the behavior of the ReLU, because the ReLU only cares about the sum of these numbers. You're preserving exactly the same function. But now if you compute the gradients and the Hessians, because you have these factors of alpha and 1 over alpha, you would see this reflected in the gradients and in the Hessian. And what you can do is you can actually manipulate, you can increase or decrease the largest eigenvalue, but when you decrease the largest eigenvalue, you make other eigenvalues go up. So you kind of just shift and change the spectrum a little bit.
Okay, great. Let's continue with the next segment. So please continue posting questions and upvote in Slido, and we will have another break for questions at the end. So Razvan, please resume your presentation.
Okay, well, thank you. Thank you for the great questions. Okay, let's see how this goes on. So parameter sharing. So let's take a simple problem. This was like one of the big successes in deep learning. Image classification, right? So you get all these kind of images and you'd want to classify them. And, we have so many different types of cats and so many different types of, you have the same cat, but you can have the cat in so many different positions. So the question is, how do you build a model that can robustly classify these things? So obviously, from the universal approximator theorem and all of these things, you can definitely learn this with a large enough model and large enough data. But the problem is the amount of data that you need to infer all the parameters to do this becomes untractable. So one thing that you can exploit is that, well, in image classification, for example, what you care about is particular features to be at a particular relative position to each other. But the cat itself, if you transpose the cat in the image, if it's in the left corner, if it's in the right corner, if it's the bottom, they should not affect how your model predicts. So you need to be position invariant. So the idea of the
again, sorry, could you please press resume presentation, because it seems like your slide is not full.
Oh, sorry. Yes. Sorry, just give me a second. Is now okay.
Yes, I think this is okay now. Thank you.
Okay, perfect. Is what am I doing here? Sorry. Yes. Okay, now it works. So one way you can do this is through convolutional neural nets. So this was one of the architectures, one of the early architectures that actually lead to a lot of success stories. So in convolutional neural nets, the inspiration came from neuroscience, and it's this idea that what you want to do is you want to look at patches of the image, and you want to ask the same questions for every patch. So you want to ask, okay, is there a cat here? Is there an eye here? Is there a nose here? And you don't actually care where this you don't care about the position, which patch has the nose, but what you care about to do your classification is to see, okay, was there an eye, was there a nose, and maybe what is the relative distance between the eye and the nose and the mouth and so forth. And if these are somehow within some bounds, then it must be that this is a face, or this is a cat, or a car, or whatever you wanted to do. So the way convolutional neural nets do this is by basically convolving these filters. So these are basically the filters are these feature detectors that you want to apply different positions. So you apply the same ones at every possible position on the image. And I was trying here to sorry, let me get my okay. So I was trying here to contrast the MLP to the convolutional. So in MLP, each pixel has its own independent weight that needs to be learned separately. In a convolutional neural net, you have this the pixel weight is so kind of like you have this filter that are repeated all over the place. So you have this repetitions of the same exact weights that you apply at different positions of the model. So this is like a visual way of thinking of how this works. So this is a structural prior that we're imposing. So this is we're introducing domain knowledge into the architecture now, and we're saying that the role of a pixel is defined by its neighborhood. So you need to look at neighborhoods to kind of decide what's happening in that part of the image, and you want to have the same function applied at all these different positions. And these functions, you can think of it as a particular feature detection. Patterns in the parameters. There was some recent work that I found kind of interesting. Yeah, if you'll have the slides, you can look at it. So it's nice to also, like we're talking a lot about this partitioning the space into linear regions. So there's a question of how a ConvNet partitions the input space. And it turns out, I mean, obviously, because we've introduced a structure, it turns out that it partitions the space in a very regular way. This kind of gives you a sense in sort of what are the difference between this kind of models. So in particular, ConvNets end up having this cones that are centered around the same point, and they can rotate and change their aperture. And this is sort of what the filters can do. And we're just exploiting here the fact that the vision problems that we're trying to use, if you look at how the data is distributed in the space, has a very particular regular shape, and this kind of partitioning of the space matches that, so that makes it work much better. But of course, yeah, the other thing when it comes to ConvNet, it's size. So it turns out that once you replace things with ConvNets, then you have this structural bias that helps you be able to process images better, but you also allows you to grow the model size quite a bit. And I think the latest thing, or the one thing now that's quite popular, is using resnets. So these are models that have hundreds of layers, or maybe not all of them, but yeah, they can range from 18 to like 100 layers or more. The point is, the nice thing that these models show for deep learning is, as we grow the model, things seem just to get better. And I just wanted to highlight that, and I'll come back to this, that one thing though that you need to do when you do ResNet is you need to use batch norm. So it turns out that if we increase the model size, then we might run out into optimization issues, and then just the gradient descent that I was talking about might not be sufficient. In particular, like one solution that's been exploited a lot for ResNet is sort of this batch norm that is renormalizing your activations, and this helps for the signal not to vanish as you go through the many layers. And yeah, just to kind of make connection. So when you go to this many layers, I think you can start to make parallels between feed-forward models and recurrent models. And I wanted to introduce a little bit what recurrent models are, and then kind of discuss the two of them in parallel. So in convolutional neural net, like convolutional neural net, is this sort of strategy of sharing parameters, so repeating the function that you ask at all positions in the image. Recurrent net is the same thing, but it happens over the time, and it's slightly different, as in basically it sequentializes the way you can process the data. So in convolutional neural nets, you can still process the data in parallel because you're independently asking the same questions on all possible positions in the image. In a recurrent neural net, you're actually looking at each time step and the processing that you've done on the previous time step to compute your new decision. So I have here like a better picture. So one way you can think of this is if you try to what people usually refer to as unrolling the recurrent neural net in time. So what happens is you see if I have my pointer. You start somewhere with some initial state, say 0, and then you observe an input. You use this initial state and the input to compose a new hidden state. And then this itself, this new hidden state, becomes an input to compute the next hidden state. So one way I like to think about recurrent neural nets is you can think of it as having a bunch of operators. In particular, I like to think of H, instead of thinking of it as a hidden state, you can think of it as history. So what recurrent neural nets do, they have these two steps. In the first step, it's a summarization process where you take the history of everything that you've seen so far, and you take the new observation, and you're trying to compose these things together. And you're trying to get a new history that compresses all the inputs that you've seen so far. So this is the hidden to hidden transition together with the input to hidden transition. So this together form this operator that is just trying to compress data. And then you have like a readout mechanisms where, okay, I have this summary of everything that I've seen so far, and from it I want to produce some prediction. And usually this is sort of yeah, you can think of it as a readout operation, and this is usually done through a linear projections with nonlinearity. And what is interesting about this is that you know, like this was discussed earlier on in the literature, but like when you talk about RNNs and you're talking about depth, which is such an important concept for feed-forward models, and as I mentioned, you know, for ConvNets you need to go to hundreds of layers. It's a bit less clear what a deep RNN should mean, and I wanted to highlight here that there are different ways in which you can make the deep net deep. I think what most people think when they say a deep RNN is sort of this stacked version, which is I think popularized by Alex Graves, and I think is the default. But you could very well think that instead of just stacking RNNs on top of each other, when I say a deep RNN, what I want to do is I want to make this operator that is trying to summarize the entire history, I want to make this operator to be deep. And this is quite a meaningful thing to try, because if you think about it, right now in a traditional RNN, this operator that is trying to summarize, is trying to add a new observation into the summary, is just a linear projection and a nonlinearity. So this, you know, generalized, so this particular transfer function is not even a universal approximator, right? Its representational power, it's quite limited in what it can do. Because it's just this linear projection plus nonlinearity. So and this compression task is not easy by any means. So if you have complicated stream of data, trying to compress all the observations that you have to get a meaningful new history, it's a very hard task. So you could easily say, well, I want this compression function to actually be itself a deep neural net, be an MLP of sorts. So you can make the neural net deep like this, and you know, you have all the other variants. You can say, okay, I want the readout. The readout right now, it's a linear function as well, followed by a nonlinearity. Maybe the readout itself needs to be deep, and there's like many variants in between. So this just kind of shows that. Yeah, like RNNs sometimes are a bit harder to grasp than the traditional feed-forward model. The other thing that I wanted to mention is sort of this famous exploding and vanishing gradients, and usually these have been studied and introduced in the recurrent net literature, and that's why I'm presenting them here. But nowadays they're kind of applying to all models in learning. It's kind of easier to understand them in the recurrent net. So in the recurrent net, if we unroll the neural net in time. So you present it as a feed-forward model that goes from time 0 to time k. Then if you want to compute the gradients, you basically apply the same backprop algorithm that we did for feed-forward models. And the only difference is that, you know, you have to go through the entire sequence until the end, and then you start from the end, which is your final loss. And now you have to backprop through this whole chain. And this looks a bit ugly because, yeah, math ends up looking ugly most of the times. But the core point here is that if you look at this gradient, it becomes a sum. And each term sum is given by the gradient of the loss that I call C in this particular place with respect to the hidden state, multiplied by this Jacobian that goes from hidden state at time t to hidden state at time t minus k, and then multiplied to the Jacobian that goes from the hidden state to the weights that you're trying to minimize. And the key component here is this Jacobian in the middle, because this Jacobian in the middle is actually itself a product of Jacobians. And the easiest way to think about exploiting vanishing gradients is to kind of have this toy image where instead of thinking of matrices that you're multiplying, think that you're multiplying scalars. And now, in order to compute the gradient, you need to multiply k scalars, where k is the distance in time between where the loss happened and where you want to assign blame, where you want to evaluate the weights. And these numbers are highly correlated. And now you can think, okay, what happens if I multiply numbers all slightly larger than 1? And this is like raising to the power k, right? So even if it's 1.01, the number, if you raise it to power 50, this would grow very quickly. And the same would happen if this number is slightly below 1. So if it's 0.99 and you raise it to power 100, this would almost surely become close to 0 very quickly. And this is what the exploding vanishing gradient is all about. The issue is you get this product of matrices. These matrices are very correlated to each other. If any of these matrices end up having eigenvalues that are larger than 1, then most likely this product will end up to an explosion of your gradient. And if the reverse is true as well. If the eigenvalues are smaller than 1, then things will vanish. The other way to think about this, the more geometrical way to think about this, maybe it's intuitive. So you can think of this from a dynamical system perspective. So in a dynamical system perspective, so what happens when you exploit gradients is that you have this regions where, so if I let my dynamical system run, it will converge to a steady state, which is this kind of point attractor. And here, what happens is I have a complicated steady state where I have two different point attractors that I can converge to. And if I'm on the boundary between the basin of attractions of these 2 points of these 2 point attractors, if I make a small change to the parameters, no matter how small, I'll basically end up moving in a different direction, and the gap would be large. So the explosion of the gradients happens if you cross this bifurcation boundary in dynamical systems. So this is one way that it was originally introduced for people who like to think about dynamical systems. If you like to think about curvature, I like sort of this kind of picture. So I think traditionally when people talk about geometry and curvature and ill-behaved curvature, they think about this kind of valleys, and this is the typical image you see in an optimization book, and you're talking about jumping from one side of the valley to the other side of the valley. I think for RNNs, the loss surface looks a little bit more like this, which is the same as this valley, but it depends on the scale and how you view these things. But the point is, what happens is you have this wall of high curvature, and then you have a very wide area of low curvature near you. So you're taking these small steps and everything is fine, but then once you take one step, you might hit this wall, and this makes you jump really far. And you can jump really far and break sort of the learning process. So the only solutions that we have so far for exploiting gradient problem, the only solution that really works so far, as far as I'm aware of, is gradient clipping. And this is now the default for when you train recurrent nets, and it applies for LSTMs and all variants of recurrent nets because they all suffer from this. And actually, people are starting to use gradient clipping even in feed-forward models. So it's definitely been used in RL. You could potentially use it for resnet as well, and it's just sort of like a safety net that you need to have when you have gradients that need to be computed over many function compositions, because you can have this explosion going on. So this is the exploding gradient problem, and then you have the vanishing gradient vanishing gradient go to zero. One thing that people might not that underestimate with the vanishing gradient problem is that the actual problem is not that the gradient goes to zero. I mean, that's sort of how we phrase it, but the gradient itself doesn't go to zero. So what happens is the gradient itself is a sum of terms, and certain terms in this sum, they would go to zero, some of them would not go to zero. So if you look at the gradient that you get after you do backprop through time, the norm of the gradient would not change. Certain terms from that gradient would disappear. And the problem is, in order to compute the gradient in an efficient way, you can't actually compute these terms separately and then sum them, just so that you see that certain terms are zero and certain terms are not. So the way it works, it kind of computes efficiently the sum, together. So you cannot analyze the terms separately. So this makes it as a very hard to deal with problem, because it's not easy to diagnose sometimes. So it's easy to see behaviorally. So if you train a model that is suffering from vanishing gradient, what you'll notice is that the model cannot connect events that are happening far away in time. But that doesn't mean that the model doesn't learn. It learns, but it learns to only use short-term information and not long-term information. Yeah, I guess going back, the other thing that is worth stating here is that when you are in this vanishing gradient regime, so when the largest eigenvalue is smaller than 1, again, if you look at the dynamical system perspective of what the RNN does, is what it means is if I send an impulse provide an impulse as an input to the RNN and then let the RNN run, over time this would go to zero and everything would converge to zero. So if you're looking at the behavior of the RNN from a dynamical system perspective, it has a single fixed point attractor at zero, and then and that's sort of not what you want, because that means that the RNN has a very simplistic behavior. What you want is for RNN to be much closer to, for the for information to be preserved through the RNN. But you need to be careful, because if the information becomes magnified instead of being preserved, then you're going into this kind of chaotic regime and you're going into this kind of explosive behavior. And a lot of the literature on how to deal with this, or like early literature on how to deal with this vanishing gradient, is looking at initialization, and they're like really great schemes of how do you initialize RNNs in such a way that you're what people used to call the age of chaos. So basically be in this space where the eigenvalues are all close to 1 and information is preserved into the net and is not vanishing. And to me, I still think that the best literature to look about initializing recurrent nets to be, in this kind of good behavior is looking at the ecostate network literature. But there's works in, deep learning RNNs as well, like Ilya Suskever paper from 2013. You can fix this by initialization, and this is sort of what Andrew Sachs proposed for feed models as well. There is actually a recent trend that is trying to constrain the learning such that it's not that at initialization you have these properties, but you always project your model on the sphere of, or on the manifold of parameters where this property is preserved. So you want to preserve this property throughout learning. So these are the orthogonal RNNs and variants of it. So there's many different techniques of how projections, but you take net and then you move away from this manifold of RNNs that preserve information, and then you have a projection step that gets you back to the manifold. I think a question in this space that hasn't been discussed as much is a question around representation. So once I feel like a lot of these works are focusing a lot on learnability and focusing a lot on gradient flow and making sure that the gradient can flow through learning, but they do not discuss whether how did you affect the expressivity of the neural net? Can you represent the same things? And I just wanted to highlight a point here that I think one reason why conv nets are so great in images is because they throw away a lot of information. I think the fact that they're able to throw away a lot of information is crucial for them to be able to work. And the same might be true for RNNs, right? RNNs, in order to solve complex tasks, in a robust way, they need to throw away information. So if you try to constrain the weights in such a way that you cannot forget anything that you see, then you'd run into trouble. So actually, I think orthogonal RNNs, they work really well in practice. I don't want to say this is the wrong way to go about it, and I think a lot more research is needed to be done in this space. I just wanted to highlight that I think the question of expressivity hasn't been studied as much in this space. A relaxation of this work, of this idea of enforcing the RNNs to stay on this manifold where you preserve information, is the idea to add this as a soft constraint. So this is a bit relaxed, because if the loss really wants you to forget, then you can do that, right? Because it's a soft constraint, it becomes sort of like, depends on the weight of this regularization term that is trying to force you not to forget. You can do a kind of a trade-off where you decide how much you want to do these things. It might also be, and I think this is also a crucial point, that it's only through the training process that you care about remembering things, because during the training process, you want to find these correlations between events to figure out exactly how you're going to solve the task. So it could, if you phrase this as a soft constraint, as a regularizer that you add to your loss, then what you can do is you can have this constraint to be strong in the beginning when you're trying to find out useful, and then you can zero out the weight of this constraint towards the end when you're just fine-tuning and you're in the later stages of learning. So this is just another way you can deal with this. I wanted to go back to feed-forward models. So in feed-forward models, initialization is super important as well. It's actually super crucial. And there are different schemes out there, and actually, annoyingly so, even though there are a few ones that everyone knows about, then different libraries actually take liberties to do certain things slightly different. I remember there was a point where there was a big discussion whether the biases should be initialized to 0 or not, and it seems that different family of libraries that were available were taking different choices. So this was some time ago. So it was at the time where Tiano was still a thing, and I know Tiano used to make biases 0, and Torch used not to, and this made things hard to compare sometimes when you would run things. So one thing that people have done in deep learning, and this comes, I don't know exactly where the root cause for this is, maybe from the fact that usually a lot of things are introduced from a probabilistic way, is that people were looking at variance. So instead of, like in RNNs, when we were talking about preserving, information and making sure that gradients don't vanish and whatnot, we're talking about any given gradient, right? You're looking at the worst case scenario. So you'd say, for any kind of input, I want to make sure my gradient does not vanish. In deep learning, though, the approach that was taken early on was slightly different, where people were looking at things in expectations, and you're looking about, okay, maintaining variance. If I provide inputs of particular variance, I want this variance to be maintained in the hidden representations that I get through the net. And Xavier Glorot and Hemingway, which are like two of the popular, I guess Hemingway is now the default initialization in feed-forward models, they were trying to maintain this kind of variance. And I think maintaining variance is fine when you don't have a very deep model. It's probably a good starting point, but it actually breaks down when you have very deep models. And I just wanted to point out this work from Soham and Sam Smith, that it's an archive that talks about resnets and batch norm. And the point is that they're trying to figure out. So one thing that is becoming apparent nowadays is that you can't really train a resnet without batch norm. Like if you remove the batch norms, even though you've initialized with Hemingway, even though you use the latest optimizer or whatnot, usually you can't really learn the resnet. And they were trying to figure out what is the role that batch norm plays. And then there's like many papers that are trying to understand batch norms, and there are different angles to it. Some people argue that it has something to do with curvature and kind of tries to approximate something like a second order method and different things. But the observation that Sam and Soham did is that actually the role of batch norm is to correct for this initialization issue, that we're looking at expectations rather than the worst case scenario. And in particular, what batch norm does is that If you think of all the different pathways that you can take through, so in resnets, just to I didn't explain this very properly, but in resnets, what you have is you have these blocks that are repeated, and for each of these blocks you have a skip connection, right? So the way information can flow, it can either go through the block that goes through these nonlinearities and linear projections, or it can go through the skip connection. And this kind of gives you like many different pathways that you go from the input to the output. And what batch norm is trying to do is trying to make sure that or like what it does implicitly, it makes sure that at initialization, the deep ResNet, the 100 layer ResNet, information like the gradients don't vanish, like the function itself behaves closer to identity, and the way it does this is by penalizing very long pathways. So so the longer the pathway, it gets penalized a lot more. So what you end up doing is you're basically trying to learn through the short pathways that are not where information is not vanishing as much, and is not exploiting either, because the gap between the worst case and the expected case, at initialization, this gap becomes larger and larger the longer the path the longer the path is. And in particular, in their paper, they showed that what you can do is you can replace the batch norm by a scalar that you use. So you buy just a particular initialization, and then you can train this deep ResNet. Like, you don't get exactly the same state-of-the-art results. So there's still aspects of batch norm that we don't cover, but you get competitive results without batch norm by just adding the scalars that kind of correct for the way the model is initialized to take better care of the worst case scenario rather than the expected case scenario. And then just a last point that I wanted to make on this is initialization is super important, and it's I think it's one aspect of learning and deep nets that needs a lot more attention and is getting a lot more attention. And I wanted to mention a few random works in this space. So one thing is, as I said before, if you move away, far away from the initialization, you can find trivial ways to break learning completely. So you can construct as bad local minima as you want, trivially far away from the initialization that we use. So initialization is super crucial for learning. This is the paper here on the left corner. Initialization, plays a big role in new theories around how learning and deep nets work. So if you heard about NTK and stuff like this, or the lottery ticket hypothesis, they all kind of rely on this idea that a lot of the solution that we're finding with these new nets depends a lot on how initialize the model, and if these models have these lucky tickets that actually need to be discovered and so forth. Happy to discuss about this to the NTK and the lottery ticket hypothesis in the chat later with people who are interested in these things. I wanted to also give a shout out to the work of Ash et al. On the difficulty to warm star neuron training, and also there's some recent work by Tudor Berariu, who was a participant to EML last year, I think, that kind of shows that actually if you pre-train a neural net, even though you're not affecting the optimization aspect of it, so you can still, the pre-trained model, you can fine-tune on the same task or a new task equally well, you're actually affecting the generalization of the model. So it seems that the generalization itself is heavily dependent on how you initialize the model. And you can easily initialize models of, just as if anyone wants to play with this, take a neural net, make the output weights like 1,000 times larger than all the other weights in the model, and try to tune this with Adam. And what you'll see is that you'd manage to reduce the training error, maybe even to zero, but you're not going to be able to generalize. So you can, based on initialization, you can move between learning and memorization, and you can tweak sort of the behavior of the learning process. The other big point I wanted to make, and this is specific for RNNs, but it's something I like to bring up from time to time. When we talk about long-term, we talk about vanishing gradients, we talk about all of these things in relation to being able to memorize things, right? So you want the gradients not to vanish such that you can have long-term memories, and you can use those to predict things. I wanted to say that the fact that the gradients flow through a neural net doesn't mean that you memorize events. In particular, the simplest example, think of a sum, right? So if you look at the sum of n numbers, if you look at the gradient with respect to any number, that gradient is going to be 1. So the gradients flow. But if you're trying to predict the numbers that are from the sum, you're trying to predict the numbers that you've added, you can't do that. So memory as a whole is a much more complicated concept, and it's not just about allowing gradients to flow in order for you to have long-term memories. But at the moment, this is the biggest issue that we have when it comes to long-term memory. So that's why all the literature is focused on this. But I just wanted to highlight that just having gradients flowing, it doesn't mean that you're actually able to memorize a lot of things. You have a lot of pathological cases, like this particular case with the sum. I was talking about those things because I think they're extremely interesting, but the workhorse of recurrent models right now is things like LSTMs. And this is yet a different way of trying to solve this vanishing gradient problem. So this is taking more of a structural way. So all the other things that I've mentioned, they were trying to change the learning approach, right? They were trying to change the initialization, they were trying to add regularization terms, add projections to your updates, but preserve the network as it was. LSTMs, what they do is they do a structural change. And I think it's been a story that happened many, many times. Somehow changing the structure of the model works better than trying to change the learning process. And it's a bit frustrating for people working on optimization and all this kind of stuff, but this is something that's been happening over and over through the literature. And in particular here, you can see that you have this update to the cell in the LSTM. So in the LSTM, it's a very complicated object, but the point here is you have all of these gates that you're computing, and they're controlling how information flows through the cell. And the important bit is that this cell update, which is sort of the content of this LSTM cell, is in this C state. This update is linear. So the fact that it's linear, it means that the gradients would flow through it, right? Because the Jacobian would be 1. And the way you make sure that you don't get to this pathological case that I was saying before, where you just sum n numbers and you can't figure out which one is it, you have these gating mechanisms that are actually protecting what information is allowed to go into the cell. So the toy example of how LSTMs are supposed to work that was given in the original paper is more, think of it as a box, where you have this gate that decides, okay, which information is allowed to go in the box and which not. And you're allowed to go some information in the box, and then you close the gate, because if you keep it open, that information will be corrupted and you're not going to be able to remember anything. And then there's another gate that decides, okay, when I'm going to allow this information to go outside of the box. And there's another gate that says, okay, when I'm going to reset the information in the box, when I'm going to make it 0, so I can add another observation into it. So this is sort of the high-level intuition. So it's this sort of discrete kind of behavior. Just obviously, this is not how it works, because this is a continuous thing. So you don't open and close doors. It's actually, you always mix things together, but as a high level picture is quite useful. The GRU is relying on the same exact intuition, but it just simplified a bit the LSTM cell, in the sense that they've reduced the number of gates and they've kind of coupled them in a different way, but it's roughly the same thing. And I should have, okay, if I highlighted the wrong part of the equation. This one was the one that I wanted to highlight it. The nice thing here is what the GRU does is it ties the forget gate and the input gate. So it's now 1 minus z and z instead of being 2 independent things. And the nice thing here is it also highlights another way of trying to understand this kind of models. So if you look at this formula, for people that are familiar with, this is the formula of a low pass filter. So, and then this is true for LSTMs as well. And actually in LSTMs, you can tie the gates and you're not going to lose any kind of performance in how the LSTM works. And then you can think that the way the GRU and maybe LSTMs remember things is by changing the cutoff of this low pass filter, right? Making it to work at a much lower time scale, and throwing away high frequency information. So this is sort of one way to think about these things. They're not really like and it's not a one-to-one match, but there's definitely some interesting aspects in trying to take this sort of signal processing view. And you can think of wavelets. You have this reset gate that gives you finite support over which you compute this integration. So there's like some really interesting parallels there, and you can also try to augment the cell by making it into a bandpass filter and all of this kind of stuff. There is some literature on this. I don't think any of them really work compared better than the original thing, but I think there's definitely something interesting there to think about. There is yet another class of approaches that I'm not going to get into, but these are things that use external memory. The most famous ones would be memory networks, and then you have the neural Turing machine. I think they tend to be somewhat finicky, and they're not sort of mainstream right now in terms of using them in big applications. However, they kind of give you a basis to build this kind of complementary systems that I was talking about, where you can mix non-parametric and parametric models. And I think there's definitely something quite useful in this space. And for very particular tasks, they work really well. It's just they're not as easy to train as a typical model, and that's why they're not as widely used as LSTMs. Last thing I wanted to say is we talked about recurrent net and we talked about convolutional nets. And the key in here is we added a lot of structural bias. We added domain knowledge by fixing how we repeat the weights. Like you can take all of these models and try to view them as an MLP, and then it just becomes different patterns in how you repeat these weights. So there is yet another family now that is becoming super popular, and Petar is going to talk a bit more about it, and Lukash as well. So these are graph neural nets, and in here is basically gives you a lot more freedom in how you repeat these functions everywhere. And just maybe I didn't make this point clear enough. The whole point about repeating this function over the input domain is like you're reducing the number of parameters, and you're basically making it to be more data efficient. And GraphNets really highlights this because with GraphNets you are way more data efficient than if you're not, because you can when you have unstructured data where the ordering of events doesn't matter. If you try to learn it with a classical approach, like for example, if you use a recurrent net when you order the nodes, then you need to show the recurrent net all possible orderings of the nodes so that it learns to be ordering invariant. And GraphNets like already encode this in their approach. And I like sort of this phrase that I think Peter used to say a lot when we were working on interaction nets, which is a particular type of graph nets. Graph nets is all about making infinite use of finite means. And I think the quote, I forgot from whom it is. It's a famous quote that probably you guys know better than me. But that's all about that's sort of the big idea behind them, right? You have these functions that you repeat in different ways, different places. So you have this finite means because you have a very few types of edges, and the types of edges are these functions that you repeat, but you can compose them in many, many, many ways, and then it gives you the infinite use. So in convnets, if you're thinking of the convnet, so you have this kind of repetition where you have where each pixel gets its own weight, but it's each pixel of a patch, and all of this this function gets repeated everywhere. In graph nets, I'll start with graph conv nets and interaction nets as well. What happens is that each pixel is treated identically, so you can't you can't know if a pixel was on the left or on the right. These graph nets always, or most of the time, they're not applied to images, but I'm just going to keep that kind of story to talk about pixels because it makes it easier. And then the only thing that, so each pixel is treated identically, and the other thing that you can change is not the spatial locality that matters anymore. You can provide the connectivity, and it can be anything that you want. So usually in graph conv nets and interaction nets is assumed given to you, or you have it and you provide it to the model. The other way to approach this is by using attention. So attention is sort of like an old idea that's been around and was used for recurrent nets to try to solve the vanishing gradient as well, by saying that instead of just looking at a history you can actually look at all the inputs that you've seen so far. And the way you do that is by you're trying to attend. So you're trying to predict which of the previous inputs you want. So this gives you this kind of softmax mask of weights that you're looking at. So this kind of attention mechanism has been brought back, and it's becoming like a key feature of graph nets. So you have it in graph attention nets, where instead of you providing this connectivity pattern, actually the attention mechanism is trying to figure out which pixel or which object is connected to which. And it's also like a building block of transformers, which you can have as a graph nets that have like a fully connected graph, and they're using a particular type of attention of deciding which word is going to look at which other words in order to decide its meaning. Okay, and then yeah, I haven't even mentioned this, but there are like different branches of machine learning, right? So we've been talking a lot about supervised, really talk about unsupervised learning. Those, many of the tools I've discussed are related to that. There's also reinforcement learning. You'll hear from Diana and Doina about it. And there's like a lot of other topics that I would have loved to talk about, like meta learning, continual learning, you know, compression and sparsity, and sort of Bayesian deep learning, and reframing the whole thing that I said so far from a probabilistic framework. But there's so much one can cover in 1 hour. So yeah, happy to chat on Rocket Chat with anybody who's interested in these things.
Okay, great. Thank you. I hope we could clap. I'm sure everybody's clapping. The great lecture. So there are a lot of questions actually in Slido, but we won't have time to go through all of them. I will just go present so that you can see them. Okay, so I hope you can see them. So the first question is asking to point some documents that discuss this mathematical fundamentals of DNNs, but maybe this we can take it offline and post somewhere this list. So second, any set of rules which we should take care of while designing CNN architecture from scratch instead of designing randomly, like in terms of number of layers and number of parameters, I imagine, and so on.
Yeah, I mean, I think size definitely matters a lot for this kind of architectures. And when you're at really large sizes, when you're thinking of like hundreds of layers, then it becomes really hard to experiment to figure out the right architecture and structure. So again, I would just go with existing models. And yeah, just if you like, I would do structural changes if you have a really good reason for it. If you have, like, I don't know, if you have some theory or some intuition of what exactly you want to achieve, but just playing with number of layers and stuff like that, just to see if it improves the number, I don't think that's feasible or useful.
Okay, intuition about what type of nets we can combine in a multitask learning problem.
So I guess you know, for any kind of model, you can train it in a multitask learning. I guess the question is whether some are better than others. So in multitask learning, one thing that you find is sort of this interference problem where you know, you would put them together, you'd hope to learn faster because they can reuse the representation, learn from one to each other. But many times they're just slowing it down. One task is slowing down the other. So you need to go at things that are trying to deal with this interference. And I don't necessarily have good reasons. I don't necessarily have good ideas right now. I think maybe a mixture of experts kind of thing, some kind of gating, things like this can help a little bit in multitask learning to reduce interference.
So you've touched on transformers. So Burak is asking, what do you think of transformer-based models thinking over RNNs for sequence tasks? If you could compare them, so you already, but if you could comment where RNN are still the preferred ones.
Yeah, so this is a great question. So I have this thing that I might be proven wrong within the year, but I have this feeling that transformers are really good when what you care about is if some events happen or not in the past, but are really bad when it comes to the ordering of events. Because they rely on this attention mechanism, so it's really hard for them to, if the prediction depends only on the exact ordering or detailed exact ordering of many events, I think transformer will struggle, and I think RNNs would not struggle with this. But I'm pretty sure I'll be proven wrong within the year by somebody.
Okay.
So.
So we are actually very late, but there was an issue with the sound, and people lost sound for about 30 seconds after the slide. If you could go back to your slide, the one at the beginning of this segment, comparing MLPs with CNNs.
Sorry. Let me open the slide. Sorry, I closed my slides.
Okay, then maybe we can just move on, and
Okay.
if it takes because we are a bit late anyway. Okay, if you have them, so if you can go back, like at the beginning of the segment when you started with CNNs.
Yes.
After
This.
after this one.
Yes.
Here. So if you could just repeat the previous one and this one just very quickly.
Yeah, so all I wanted to say is that ConvNets here, they're introducing a structural prior. So basically they're saying that the role of one pixel is given by its neighborhood. So this is sort of domain knowledge that we're introducing model and function. So you're thinking about like a feature detector that you want to apply at every position in the image, and you want to ask, is there an eye anywhere in the image, and is there a mouth anywhere in the image, and then maybe you care about the relative position of these two things, one of each other, and that helps you to classify. But you don't care the exact position where the mouth is. You don't care if it's in the left corner, in the right corner, or whatever. And the other thing I wanted to say is like, an MLP can reproduce a ConvNet. If you have the weights of a ConvNet, you can reconstruct the MLP. That would be exactly the same function. But if you look at the weights of that MLP, they're highly structured, right? They have a particular sparsity pattern, and the weights repeat in a particular way. And this is really hard to learn by stochastic gradient descent. And then that's where the domain knowledge helps you, right? It reduces the search space in such a way that you can find these very structured solutions that you would not be able to hit with SGD if you try to learn in MLP. So in MLP, you'll probably never be able to learn MLP to behave exactly like a ConvNet, even if you have lots of data, just because of the accuracy that you need to get this perfectly.
Great. Okay, thank you. Maybe let's just take two more questions,
Yeah.
and we'll take the break. So next, is somehow the sharpness flatness of the minimum related to the uncertainty of neural network predictions?
There is a connection there. I don't think it's the only aspect of it, but it's definitely, at least for classification, if you have a softmax, the more certain you are, you need to drive the softmax to saturation, which means that you need to grow the weights, which would implicitly grow the curvature as well. But you could still have high curvature in an uncertain model.
Okay, so and maybe the last one. Almost all CNNs use pooling layers. However, the AlphaGo paper does not use pooling layers. Is there a reason for not using pooling layers?
So I think pooling is becoming. I'm not the vision expert, but I don't think pooling is as relevant as it used to be a few years back. Resnets don't really use pooling, as far as I'm aware. Again, pooling was mainly used there to reduce computation. So the big advantage of pooling in the early years was computational. As we have better and better hardware, computation is becoming less of a reason, so people are not using pooling as much.
Okay, thank you. I think we will stop here because we are late. So there is still a large number of questions in Slido, and Razvan will try to answer those offline. We'll probably take them over Rocket Chat. So next, we have the poster session. So please, the presenters for the session 1A, B, and C, please be online and answer questions in the chat windows. So, and we encourage all of you to go and visit the posters in session 1. So you will have time tomorrow and the day after to visit session 2 and